Okay, so we're just going to go through some OCR A-level chemistry exam questions from various papers on Equilibria. Okay, so when the indicator bromothymol blue, which can be expressed as HIN in the formula, so that's the indicator bromothymol blue, and that's the colour yellow. And then it dissolves in water and the following dynamic equilibrium is set up. And then this species, IN minus, is blue plus H plus. Okay, so when the indicator bromothymol blue, which is expressed as HIN, dissolves in water, the following dynamic equilibrium is set up. The indicator solution appears green because it contains both the yellow, HIN, and blue. So it actually looks a green colour because it's a combination of yellow and blue. So this is question A. I'm not quite sure which year this is from. This is from an old OCR A-level chemistry exam paper. State two features of a dynamic equilibrium. So state two features of a dynamic equilibrium. And that's the question. Okay, so there's actually three features you can give. You can say that the rate of the forward reaction equals the rate of the reverse reaction. So the rate of the forward reaction equals the rate of the reverse reaction. And that's how you know a reaction is in equilibrium, is in dynamic equilibrium. You could also say that the reaction needs to take place in a closed system or an isolated system. That is a possible answer as well. Okay, the reaction can only take place in a closed system, or you can use the term isolated system. And also, if the rate of the forward reaction equals the rate of the reverse reaction, it appears that the concentration of the reactants and the products are constant, that they are not changing. Okay, so for the answer to the question, state two features of a dynamic equilibrium, there's three possible answers you could have. You could have forward rate equals reverse rate, it takes place in a closed system, or the concentration of reactants and products are constant. Part B, state Le Chatelier's principle. So this is Le Chatelier's principle. Okay, so this is just a definition. State Le Chatelier's principle. When a system in dynamic equilibrium, let's put equilib. When a system in dynamic equilibrium is subjected to a change, the position of equilibrium will move. I'm just going to put POE. The position of equilibrium will move to minimize the change. So in an exam, you don't write POE in an exam, write position of equilibrium. And I'm just doing it quickly, yeah? So it says state Le Chatelier's principle, it's a definition. There are 2 marks for it. When a system in dynamic equilibrium is subject to a change, the position of equilibrium will, there's no comma there, the position of equilibrium will move to minimize the change. That's part B. Okay, part C. So hydrochloric acid is added to the solution above, okay, the indicator. So hydrochloric acid is added to this equilibrium until no further change takes place, okay? So you're adding H plus to the equilibrium, to the indicator solution, which is shown above. Use Le Chatelier's principle, suggest and explain. So you've got to suggest and you've got to explain it using Le Chatelier's principle, suggest and explain what colour change you might see. Okay, suggest and explain the colour change. Right, so we're going to add acid to this equilibrium. Okay, so if we add acid, it's not an equilibrium anymore. Okay, so using Le Chatelier's principle that the equilibrium has to move to minimize the change. We add acid, it's not an equilibrium. We have to remove the acid. So the position of equilibrium will move to the left. Remember, this is the left and this is the right as you're looking at it. So we add this, the position of equilibrium move to the left to minimize the change, and the solution will turn the color yellow because that's the color on the left. So you add acid, not an equilibrium anymore. Le Chatelier's principle states that the equilibrium will move to minimize the change. It'll move to the left. The color yellow is on the left. Okay, so you just need to write that down. So you add H plus. Okay, so you add H plus. You add H plus. This will move the position of equilibrium. Position of equilibrium moves to minimize the change. This is using Le Chatelier's principle. Therefore, moves to the left. Moves to the left. Whoops, sorry. Moves to the left, and the solution will be yellow. Will be the color yellow. Okay, the solution will be the colour yellow because that's the colour on the left. Will be the colour yellow. Okay, part D. So to this equilibrium again, this is part D. Okay, so you add sodium hydroxide, aqueous sodium hydroxide. Aqueous sodium hydroxide is added gradually to the solution in C. Okay, so it's this solution in C. So it's yellow. It's colour yellow. Yeah, it's a yellow colour. And we're going to add sodium hydroxide to the solution of C until no further change takes place. So what's going to happen now? Okay, so if you add sodium hydroxide is going to react with the acid because sodium hydroxide is an alkali. So sodium hydroxide will react with the acid to form water. Okay, so sodium hydroxide will react with the acid. It will remove, so it's effectively removing the acid. The equilibrium will move to minimize the change. The position of equilibrium will move to the right to restore the acid, and so you will turn the color blue. Okay, so if you add sodium hydroxide, the sodium hydroxide will react with the acid, and so therefore effectively it is removing the acid from the equilibrium. It removes the acid from the equilibrium. So the equilibrium will move to the right to restore it. The position of equilibrium will move to the right to restore it. And the solution on the right hand side, the solution will turn blue. And you need all of that for the marks. Okay, the solution will turn a blue colour. Okay, so that's the first exam question. Right, this is a different exam question, still from an OCR A-level paper, A-level chemistry paper 2. Okay, so this question is about calcium carbonate. Right, so if calcium carbonate is heated strongly, okay, in an open container, so this is an open container, so it's not a closed system. It's an open container, it's not a closed system, and you heat it strongly and it forms a thermal decomposition, and the enthalpy change is plus 180 kilojoules per mole. Okay, it's called thermal decomposition. Thermal decomposition, because you're using heat to break it down. Thermal decomposition. Okay. First question, this is question A. Suggest 2 reasons, you need 2 reasons. Suggest 2 reasons why it is necessary to heat the calcium carbonate strongly to achieve decomposition. So 2 reasons why we need to heat strongly the calcium carbonate. Okay, why? In order to get in order to decompose. So the first reason is that you need to heat strongly in order to break the bonds, because you have to break the bonds. First thing you do is you have to break the bonds. Okay, and the second reason why do you need to heat strongly? Well, this is an endothermic reaction. So endothermic reactions overall, they need an input of energy. So we can just simply say this reaction is endothermic. It needs an input of energy. The reaction is endothermic. There is a third possible answer you could give as well. Endothermic reactions have a higher activation energy than exothermic reactions. So you could say to overcome the activation energy. Endothermic reactions have a higher activation energy than exothermic. So you could say to overcome the activation energy. Okay, so part B to this question, part B is do this reaction again, but this time do it in a closed container. So it's closed, all right? So you can do it again, but closed this time. It's heated strongly, and the equilibrium is set up because it's in a closed, so an equilibrium can be set up now. Okay, this is part 1, what can you say about the rates of the forward and reverse reactions when the calcium carbonate starts to decompose? Okay, so what can you say about the rate of the forward and the reverse when it starts to decompose? So not at equilibrium, when it starts to decompose. So initially, the rate of the forward is going to be faster. It's faster than the rate of the reverse. Okay, so initially the rate of the forward is faster than the rate of the reverse. Okay, so initially the rate of the forward is faster than the rate of the reverse. Okay, then part 2 says, what can you say about the rate of the forward and reverse when the equilibrium has been established? So when you've reached equilibrium, when equilibrium has been established, when you've reached equilibrium, what can you say then? Well, then we can say that rate of the forward equals, rate of the forward, so I'm writing, equals the rate of the reverse. I'm trying to write quickly. Okay, so initially, that's going to be faster, but then at equilibrium the rates are going to be equal to each other, because that's one of the characteristics of an equilibrium. And then the last part, part 3, a valve, it's like a tap, a valve allows some carbon dioxide to escape. So carbon dioxide gas escapes from the equilibrium, okay, the valve escapes. State and explain, this is state and explain, for the mark, state and explain what happens to the composition of the mixture. So they want to know about the composition of the mixture in the container. So composition means what is it composed of? What is the mixture made up of? What is it composed of? Okay, composition of the mixture. Right, so carbon dioxide is allowed to escape, right? So carbon dioxide is allowed to escape from the equilibrium using a valve, using a tap. So the position of equilibrium, if it's allowed to escape, you're removing it. The position of equilibrium will move to the right to try and restore it. And that will lead to more calcium oxide and less calcium carbonate, because you're going to move to the right, okay, to try and restore the equilibrium. So the answer is, so if you allow the carbon dioxide to escape, the position of equilibrium will move to the right, to restore the equilibrium, and that will mean that you're going to have more calcium oxide formed. Or you could say less calcium carbonate in the mixture. But you've got to mention the composition of the mixture. What is it made up of? Okay, right, one more exam question, last one. One more exam question, equilibrium exam question. So, again, OCR A-level chemistry from a past paper, all right? In the Haber process, or the Haber process, however you pronounce it, in the Haber process, or the Haber process, nitrogen reacts with ammonia, nitrogen reacts with hydrogen, to make ammonia, okay? And there's a diagram, and it goes into, the nitrogen and hydrogen goes into a reaction chamber. It's called the reaction chamber. So that's where the reaction happens, okay? And then it passes, this is the industrial process, and then it passes into another chamber, which is called a separation chamber. This is when you separate. So remember, this is in equilibrium. This is in equilibrium because it's nitrogen, they're all gases, and hydrogen, and it makes ammonia, which is a gas, and the enthalpy change is minus 93 kilojoules per mole. Okay, so they're all gases, and then you separate, and out comes ammonia. Thank you very much. Out comes ammonia, but then because it's in equilibrium, there needs to be another stage here, going in that direction, and in this exam question they've called a stage X. Okay, so that's the exam question, and it says, part 1 says, describe the conditions that are used in the reaction chamber and explain why these conditions are used. So describe the conditions used and why. Okay, this is the conditions used in the reaction chamber. Okay, describe the conditions and why. Right, so what is actually used in the reaction chamber? So let's talk about pressure first. Okay, and this is a long answer question, and there's actually 7 marks for this question because it's a long answer question. Okay, describe the conditions used in the reaction chamber and why. So first, let's talk about pressure first. So what kind of pressure do they actually use when they make ammonia through the Haber process? So they use 200 atmospheres pressure, okay, which is a high pressure. So we have to describe the conditions and why they're used. So why do we use a high pressure? So a high pressure gives a good rate, gives a fast rate. A fast rate, okay, it's going to be a fast rate of reaction, and that's why we use a high pressure. Okay, so that's 1 mark, because if you use high pressure, the molecules are close together, and so there's more collisions, more frequent collisions, more successful collisions. Okay, so why else is a high pressure used? If you use a high pressure, it's going to give a high yield. It gives a high yield of ammonia, so lots of ammonia. But why does it give a high yield of ammonia? Because there are 4 moles of gas on this side and 2 moles of gas on this side. High pressure favors a side with fewer molecules. Fewer moles. So the position of equilibrium will move to the right. Position of equilibrium will move to the right, and you'll get a high yield of ammonia. So that is good. So industrially, they use a high pressure because it gives a good rate. It gives a lot of ammonia because the position of equilibrium will move to the right. But there is a downside. There's a disadvantage with using a high pressure. It means that it's expensive using a high pressure because there are safety concerns. You know, you've got concerns, you've got gases under high pressure, you need special equipment, everything needs to be a thicker, better quality, so that is a disadvantage. But those are the 3 marks for high pressure, okay? And then you do the same for temperature. Okay, so they use a temperature of between 400 and 500 degrees. So I'm going to write 450 degrees temperature, which is a high temperature. They use a high temperature. Okay, so why industrially do they use a high temperature? So 1, high temperature will give you a fast rate. Yeah, so again, it gives a good rate if you use a high temperature. It gives a good rate. So that's 1 mark, because high temperature means that more molecules have energy greater than the activation energy, so there's going to be more successful collisions. Okay, but what happens to the yield if you use a high temperature, right? High temperature favors the endothermic direction. Okay, if we look back here, this here, that means that the forward direction is exo, so the reverse direction is endo. So high temperature will favor the endothermic. Position of equilibrium will move to the left, which is rubbish, because that means a low yield of ammonia, which is a disadvantage. That's not good, but that's a mark, okay? So high temperature advantage gives a good rate. Disadvantage, you get a low yield. So what they actually use is a compromised temperature is used. A compromised temperature is used instead. So they don't go really high. They don't go like 1,000 degrees. They don't go really low. They use a compromised temperature. It's just like between the 2 temperatures, between high and low, a compromised temperature is used. Is the 3rd mark of 450 degrees. So I said to you that this exam question has got 7 marks. So we've got 1, 2, 3, 4, 5, 6. We've got 6 already. So there's 1 more mark. Remember, the question said, describe the conditions used. We've mentioned pressure. We've mentioned temperature. The last condition that's used is what? Is a catalyst. You've got to mention a catalyst. The catalyst that is used is solid iron, and the catalyst speeds up the reaction. And just gets to equilibrium quicker. So catalyst is the last part there. Right, there's another part. That's part 1 to this question. Okay, it's nearly finished. Part 2. Okay, part 2 says, suggest, so this is part 2, suggest how ammonia can be separated from the separation chamber. How ammonia can be separated. Okay, so remember that what happens is you've got the reaction. So you've got the reaction first, then it goes into the separation chamber, and ammonia needs to be separated. So how can ammonia be separated? Now they give you some information, right? They give you some boiling points to help you with this. Okay, and the boiling point of nitrogen is minus 196 degrees. The boiling point of hydrogen is minus 253, and the boiling point of ammonia is minus 33. And they give you this information and they expect you to use it in the question. So how is ammonia separated from the separation chamber? Because remember, it is in equilibrium, and all 3 gases, they're all going to be in there. So how do you separate it? So you've got to look and you've got to think, okay, what does this boiling point, what does it actually mean? So if we've got minus 33, okay, if we go like minus 32 degrees, minus 32, then ammonia is a gas, because this is the boiling point where it turns from a liquid to a gas. So minus 32 is a gas. But if we go down, we go to minus 34, say. So if we go, that's going up in temperature, minus 32. If we go minus 34, then ammonia is going to be a liquid. Okay? So all we need to do is reduce the temperature. So cool to below minus 33. So minus 34, for example. And then ammonia is a liquid. Ammonia is a liquid. And all the others will still be gases. nitrogen and hydrogen are still gases. But if ammonia is a liquid at below -33, then you can just remove by tapping, using a tap. You can just tap off the ammonia because it is a liquid. Okay, you can just, the word is condense the ammonia is what you can say. Turn it into a liquid, and it can just be tapped, it can just be removed. Final question, part 3. Suggest what happens in stage X. Oops, stage X. What is happening in stage X in the diagram? Okay, what is happening? So we go back to the diagram. What is happening in stage X? So the reactants come into the reaction chamber, makes ammonia. Then you've got nitrogen, hydrogen, ammonia in the separation chamber, and ammonia is removed by cooling to below -33. Then what happens in stage X? This is where the nitrogen and hydrogen are recycled. There's no point wasting them. We need to bring them back around and recycle them and use them again, because it's very difficult to get hold of nitrogen and hydrogen, and therefore we need to recycle them.